Welcome to physics. Today we're going to ponder an application that involves both light and refraction. We're going to ponder the application of color. Let's think about color in terms of what we talked about back with sound. When we talked about sound waves, we talked about you hearing different sound waves, and specifically we talked about frequency. Sound waves are produced in different frequencies, and when a different frequency gets to your ears, it's converted into an electrical impulse, and it goes to your brain, and your brain interprets that frequency as a different pitch of the sound. Well, for light waves, you have a similar thing. Light waves go to your eyes, and when they go into your eyes, they get converted into an electrical signal. So sound becomes an electrical signal, light becomes an electrical signal. But when that electrical signal from light gets to your brain interprets the frequency of that light wave, and it says color. So pitch is to a sound wave what color is to a light wave. Okay, or if we think in terms of sound waves, we break those sound waves up into musical notes. And you have an octave, you have different musical notes in an octave. Well, the octave of light waves is Roy G. Biv, using the analogy. Okay, so your musical notes for sound waves are just like your colors for light waves. They are your brain's interpretation of the frequency of that wave. So then color, light waves don't have color. Light waves have frequency. And so if we're going to define color, color is how your mind interprets the frequency of a light wave. So if we consider normal white light passing through a prism is broken apart into the spectrum of colors. So then white light is really an interference pattern, as we've talked about before. It is a combination of all of the different colors in a prism due to refraction. Those colors get split apart, and you see the spreading of the spectrum there on the right side. Now, let's talk a little bit about that spreading of those colors, because that is an application called dispersion. Okay, if you look at the different colors that are there, red gets bent the least, violet gets bent the most. And so what's happening, if they're bending different, they have different indices of refraction. Up to this point, we've talked about the index of refraction solely dependent on what the substance is. But now what we're seeing is that there's a slightly different index of refraction for each different frequency or wavelength of light. If violet is bending the most, then light has to slow down the most. And if light slows down the most, then you're going to have a higher index of refraction for that violet light. If we look specifically at a chart here, it breaks the spectrum into blue light, yellow light, and red light. And if we look at, for example, flint glass, you've got an index of refraction for blue light of 1.639. Okay, that's on the higher end. That's towards violet. As you work your way across to yellow light, the index of refraction drops some. And for red light, the index of refraction drops even more. And so then red light, and the diagram at the bottom, is going to refract the least. Okay, blue light is going to refract the most. Or in terms of our entire spectrum, Roy G. Biv, you're going to refract the least on red all the way up to the most on violet. So the dispersion of light is really the spreading of these colors of light as that light passes through a prism or something of a similar shape. And it's due to the difference in index of refraction of your different wavelengths of light. Now, getting back to color, your visible spectrum, these are really different frequencies. The color does not occur until your brain has interpreted that frequency. So now if we consider different objects, take a minute, look around the room that you're sitting in, and identify different objects and what color you would say those objects are. Pause the video for a second and do that. Now, if I look around the room that I'm in, there are several different objects I can identify. I've got my cat, and we're going to bring the cat down a little bit in size here. I've got my cat. I'm going to bring a couple other objects in. So we've got several different objects here. If I was going to identify the colors here, I would say the cat is gray. The Cheez-It box appears to be red. Gizmo, our dog, we'll call him white. Okay, the cat toy is looking kind of orange. And then the Nerf gun, blue. Now, we just talked about a second ago, color occurs in your mind when your mind interprets the frequency of the light. Okay, so all of these objects appear certain colors, emphasizing the word appear, but the objects actually have no color to them. Okay, if we're talking about the color of the actual objects, all the objects would be colorless because color is not a property of an object. Color is a property of light and the interpretation of that light. Okay, if you think about saying, well, I have a jar full of whatever, zinc atoms. Atoms themselves don't have color. Okay, it's only when light interacts with those substances that they have the appearance of color. So if we take, for example, the Cheez-It box, well, the Cheez-It box appears red. So what's happening, so I was sitting in my living room, white light is hitting that Cheez-It box, and of that white light, red light is reflecting off of it. So here's the Cheez-It box. We have normal white light. And that white light we know is a combination of all of Roy G. Biv. Okay, is hitting that box. What is bouncing off of that box, what is reflecting then, would be red light. And so that red light goes to your eyes, nothing drawn to scale here, and your brain sees red or interprets it as red. So then objects appear the color of light that they reflect. A little more succinctly, here in the picture we have a ladybug sitting on a leaf. Roy G. Biv, or white light, hits the ladybug. Red light reflects off of that. Red light goes into your eyes. Your mind interprets and sees the ladybug to have a red color. Roy G. Biv hits the leaf. Green light reflects off the leaf, okay, or light that has a frequency that your brain interprets as green, and so you judge that to be green. Objects, again, don't have an inherent color, but they do interact with the light to absorb certain colors and reflect others. The ones that get reflected and go into your eyes, your mind then interprets. So then going back here to our list of objects, that'll explain why the Cheez-It box appears red, because Roy G. Biv hits it. Red is one of the colors in Roy G. Biv. Red reflects. That explains why the cat toy is orange, because orange is in Roy G. Biv, and why the Nerf gun appears blue. But the gray of the cat, gray is nowhere in Roy G. Biv. The white of our dog Gizmo, nowhere in Roy G. Biv. Those are not spectral colors, so it does not explain those objects. Let's deal with those objects specifically, and I'm going to add one more. I'm going to make a little room here. The cat appears gray. The box appears black, and the dog appears white. None of those are colors in Roy G. Biv. white light is going to hit all of these objects. So then what you need to think about is what is reflecting off of them. Let's consider Gizmo the dog first. If I have white light hitting Gizmo and he has a white appearance, that means that that white light, which is Roy G. Biv, most of the light that hits him reflects back off. So we see a white appearance. Okay, it's not a preferential orange like the cat toy or a preferential blue that's reflected like the Nerf gun, but rather it's most of all of the colors to give him that white appearance. So then if we go to black, Roy G. Biv hits black, normal white light, but if we're seeing a black appearance, there's not much that is reflecting. Now, if you look at a black object, if nothing reflected from the black object, you would not be able to see the object because nothing would be coming to your eyes. In other words, it would be a complete void or a complete absence. Well, that's not the case. When you see a black object, you're seeing something. And so then what reflects off of that black object is a low amount of everything in Roy G. Biv. So let's say maybe 10% of Roy G. Biv reflects. So it's not enough to give it the appearance of any single color, but it is enough for your brain to interpret that something is there. So then that means that gray would have to be somewhere in the middle. White light hits the cat, and the cat's name is Asuna. So Roy G. Biv hits Asuna, and then what's reflecting off is still Roy G. Biv, but it's not close to 100% like what was reflecting off of the dog Gizmo. It's not a low level 10% that was reflecting off the black object, but rather it's somewhere in the neighborhood of maybe a 50% reflection. So you're getting basically a dim white. That's what gray is. It's not a color. Gray and black are actually shades of white. White light is 90 to 100% of Roy G. Biv reflected. When you reduce that to in the neighborhood of maybe 40 to 60%, then your mind perceives a dimmer white, which we would call a gray. And if the reflection is even reduced further to like a 10%, then your mind interprets a very dim white, which we call black. So gray and black are actually just shades of white. They are reduced percentages of the reflection of all of Roy G. Biv. So kind of in summary, objects will appear the color of light that they reflect. Red objects appear red because they reflect red light. Violet objects appear violet because they reflect violet light. Any object that is not a spectral color of Roy G. Biv is reflecting some combination of Roy G. Biv, which then your mind just has to make sense of. So something that appears tan, well, that's some combination of some red and some orange and some yellow, etc., that are reflected, and your mind just has to make sense of it. So your mind interprets and says tan. One thing that affects the color appearance of an object is the color of light that is present. So up here I have our red and orange and yellow and green and blue and violet. Okay, and right now you're seeing those under white light, and white light is a combination of all of the colors, Roy G. Biv, all mixed together. So then each of these are appearing the color that they are because that color of light is present, and that's what's getting reflected back to you. When you adjust the color of light that is present, then things look a little bit different. So if I change, now what you have is red light. And so you can see the change in the appearance of the different colors because only red light is present. Some of these are able to reflect red light, some of them are not able to reflect red light. So you see their appearance under red light. To be able to compare, there's a white color bar reference as to what those colors look like normally. And I'm putting it towards the bottom because I know you're seeing a little bit of glare due to the position of the projector and the iPad. So you can see what these colors look like normally and how they appear under red light. Now, again, if we change, this is how they appear under orange light. This is how they appear under yellow light. And there's the reference bar added in so you can see what they appear like under normal white light. So I have just white coming through here, but it's yellow light up there and yellow light down here. Under green light, and again, the reference so you can see what the colors look like normally. Under blue light, and under violet light. So, objects appear different colors because of the color of light they reflect, but that is also influenced by the color of light that is present. This is used a lot in stage lighting. You can change the atmosphere of a scene just by changing the colors of light that are there. Okay, you can change the appearances of scenery. You can change the appearances of costumes. Again, if you illuminate it by a red light versus a blue light. So there's a lot of this science that is used in stage lighting. Now, let's consider mixing different colors. First of all, we have to make the distinction between a pigment and a color of light. When you're dealing with pigments, you're basically dealing with paint. Specifically, paint, pigments added to clothing and whatnot. There's basically certain atoms that will interact with light in a way to be able to reflect certain colors of light. So if you're wearing a blue shirt appears blue because it contains blue pigment. What that means is it contains atoms that will reflect light in the frequency range that your mind interprets as blue and absorb other colors. When we're dealing with pigments, the primary colors of pigment, these are things you were probably taught in elementary school or in art, but it might be a little bit different than what you've learned previously. Typically, we are taught that our primary colors of paints are red and blue and yellow. Actually, those primary colors are magenta, which is a reddish color, cyan, which is a bluish color, and yellow, which is yellow. And basically, these are the primary colors because these can be mixed together in different amounts to be able to get any different color. Now, let's illustrate the primary colors of pigment. Here is cyan. Now, when we overlap cyan with magenta, we get a dark blue color. And then when we add in yellow, we get the combinations overlapping. Notice in the middle, you have a black region. Now, that's the region where all three pigments overlap. Each of the pigments not only reflect certain colors of light, but they also absorb certain colors. This is called a subtractive process that we're going to get into more details on. The cyan absorbs certain colors, the magenta absorbs certain colors, and the yellow absorbs certain colors. What happens is that all the colors have been absorbed out by the different pigments, and in the center region you get a black. That's the same idea as when you're mixing lots of different colors of paint together. You always end up with a darker color. You never mix half a dozen different colors together and get a light color. It's always dark because you subtracted out all of the different colors of light. Now let's illustrate this with a specific combination. If we look at a simple combination yellow paint plus blue paint. If we mix yellow and blue paint together, that produces green. Think about that for a minute. You're mixing yellow paint together, which reflects yellow light, and blue paint together, which reflects blue light, and when you get them in combination, they reflect an entirely different color of light. They reflect green light. Well, there's a little bit more to it than that. So let's consider our situation here. Here's our combination. We're dealing with blue paint and yellow paint to get green paint. Now, blue paint does reflect blue, but it actually does a little bit more than that. Blue paint will absorb red, orange, and yellow light, but it will reflect green and blue and indigo and violet light. So each color of pigment may have a certain appearance, but it's actually going to reflect more than just that single color of light. Yellow paint, very similarly, it will reflect red and orange and yellow and green light, but it will absorb blue and indigo and violet. So then what happens here is anything that is absorbed by a single pigment is gone from the final combination. So then if we look at blue paint, it's absorbing red light, and so then red light is gone from the final combination. It absorbs orange light. Orange light is gone from the final combination, and yellow light is absorbed by the blue, so it's gone. Flipping over to the yellow paint, it absorbs the blue and the indigo, and so that's gone from the final combination, and it absorbs violet, so that's gone from the final combination. So then the only thing that you have that is reflected by both yellow and blue paint is green, and that's why it has the green appearance when you mix those two pigments together. Any mixing of colors of paint happens in that fashion, where you get a certain appearance based on what they both mutually reflect. Again, we define that as a subtractive process, and basically what that means is that each pigment will absorb out certain colors of light that are then eliminated from the final combination. You only see what is reflected by all the pigments. Now, mixing of colors of light, you can imagine different colors of flashlights. There are primary colors of light also. These primary colors of light you may be familiar with if you think about like the display on your phone or on a computer screen or on a TV. All of those things are typically RGB displays. In other words, they have red and they have green and they have blue pixels, and these in different combinations can be mixed together to be able to form any color of light. Mixing of colors of light together is a completely different process. It's what was referred to as an additive process. If I have yellow light and I add blue light to it, well, then I have more light than I started with because I added additional light. If I'm adding additional light, then what I should be working towards is something that is brighter. So then each color of light that is added basically stays present in the final combination. Now, let's animate mixing the primary colors of light. Here we have a red light, and when we mix that together with a green light, they overlap and they produce yellow, which is a much brighter light because we have more light present. When we add in a blue light, now notice the very center region. The very center region is white because we've added in the three primary colors of light so that we have all of the visible spectrum present, and all of Roy G. Biv present is white light. When you add colors of pigment together, you subtract out, you always work towards darker. When you add colors of light together, you always accumulate and end up with a brighter color. Dealing with applications, Combining colors of pigment, probably the place you're most familiar with that is if you've ever changed the ink cartridges on a printer. Those ink cartridges come in magenta, cyan, and yellow. So when something is printed, what you have is a cyan layer is laid down, a magenta layer is laid down, and a yellow layer is laid down, just as we see in the picture of the fruit at the top of the screen there. Now, it takes a lot of ink of those three colors to add together to get black. So usually there is a fourth cartridge of black and sometimes some additional ones also, just to be able to save on ink. So then our picture of our fruit, we see the total color appearance by the combinations of the different colors of ink that are there. And that's illustrated again on the picture below of the beach scene. When you have any printed picture, we have a picture of two children here. If you zoom in very, very closely over to the right side of the screen where you see 800% magnification, you can actually see dots. And those dots are combinations of magentas and yellows and cyans. Anything that is printed is done with those dots of those different primary colors. On the bottom of packaging, like the Cheez-It box I had just a minute ago, usually there are codes that show alignment for printing and the different saturation levels of the different inks. So if you have a cereal box, a Cheez-It box, anything, usually you can look somewhere, maybe it's under the flaps that are glued together, and you will find color code patterns like this. Mixing of colors of light together is done a lot in stage lighting, which we've talked about a little bit already, and it's done also by technologies such as any display, your phone, your computer. So here we have some different zoomed in images of digital displays, and they're broken down into RGB, red lights, green lights, and blue lights, and in different brightnesses, those give different appearances to your eyes. Focusing down here at the bottom, okay, on this first display over here on the left, you can see in the circle in the middle, a little bit of red that is pretty dim and a much brighter green. That combination is giving an appearance shown right there. When we change the levels in the second diagram here, now the red is a bit brighter, then your mind interprets it as a little bit yellower. And then similarly all the way to the right, in different intensities, your mind interprets it almost to have a little bit of an orange combination. So combining different colors of light. In summary, we just covered a lot on color. We talked about what color is. We learned that it is a property of frequency. It's how your brain interprets the frequency of the light. So color is perceived in the mind. We talked about the objects and what colors they appear. Solid objects will appear the color of light that they reflect, but that also depends on what color of light is present. We talked about mixing of colors of pigments. That is a subtractive process. Each pigment absorbs out certain colors of light, so then reflects others, and you see only the colors that are mutually reflected by all the colors of pigment. And we talked about mixing of colors of light, which is an additive process. All colors added stay present in the final combination, and so generally work to a brighter color. Ponder physics.